hello once again. So, in continuation to our earlier lecture on discrete probability distribution, where we have discussed binomial distribution, uniform distribution, binomial distribution, multinomial and hypergeometric distribution. In today's lecture, we will be discussing few other discrete probability distribution. So, what are those? We will be discussing negative binomial distribution, geometric distribution, Poisson distribution, and also finally, we will discuss the descriptive measures of all these distributions. So, first is what is negative binomial distribution. In binomial distribution, if you guys can remember, binomial distribution, what was that? Our number of trials are fixed, that was n, we have specified it by small letter n, remember that was the number of trials. Our number of trials are fixed. In this number of trials, our random variable was the number of success. So, variable is something which changes, right. So, we have taken the random variable as the number of success. So, in n trial, whether the number of success is 0 success, 1 success, and it can go for x can take value from 0 to n. That was our random variable as the number of success, that was changing. But whereas in some other experiment, what we get to see is that where the trials are repeated till we get a fixed number of success, meaning here now number of trials is not fixed, that is number of trials is not n, the number of trials can be anything, but we are interested in getting a fixed number of success. That means, suppose we are interested in getting total 5 success. So, our number of success cannot be a random variable. So, number of success is fixed here, is not it? It cannot be a random variable. Now, what is the random variable here? Our random variable is the number of trials. So, now my x is number of trials, rather number of success is fixed. That is the negative binomial distribution. That is the only difference between binomial and negative binomial. There is not a very small difference, but it is a big difference, but that is the only difference between binomial and negative binomial distributions. So, negative binomial distribution, an example, you flip a coin repeatedly and count the number of times the coin lands on head. You continue flipping the coin until it has landed 5 times on the head. Yeah, continuous. My interest is I should get 5 heads. So, I am continuing flipping it till I get 5 heads. When I got 5 heads, I stopped it. Okay. So, my number of trials is how many trials I needed to get 5 heads. So, that is my random variable. So, negative binomial distribution used to compute probability of the kth success occurs on the xth trial. K is fixed, x is the random variable. Whereas, in binomial distribution, we used to compute probability of x success in n trial, where n is fixed, right. So, that is the only difference between the negative binomial and binomial distribution. So, similarly, our definitely if this is the only difference. So, our formula for calculating f(x) will also be same, almost same. The only difference here you see, since we are interested in finding out kth success, that means my last trial will be the k number of success. So, trial before to that, okay, if my last trial is x, okay, trial before to that, that means in x minus 1, in x minus 1 I will get k minus 1 success. This can be in any pattern, as we have seen in binomial distribution how it can be in different pattern, success, success, failure, 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 success, success. I have shown one example, if you can remember. If you do not remember, please go back to the lecture again, you will see that I have walked in a blue board showing you how we have done. So, similarly here, that means on the xth trial I got my kth success, okay. That means all the trials before this xth, before this point is the x minus 1. In this x minus 1 trials, how many success I got? I got k minus 1 success. It can be in any order. So, that is why it is x minus 1 c k minus 1, okay. And total how many success are there? Definitely I am looking for k success. So, total it will be k p to the power k, and how many unsuccess? That is 1 minus p, that is q, q is x minus q, q to the power x minus q. This is the formula for, so this is the formula for binomial distribution, negative binomial distribution. So, we will see an example. A website contains 3 identical computer servers. On these servers, various requests are made by the customers. The probability of a failure of server is 0.0005. Okay. The probability of, that is the probability of failure. assuming that each request represents an independent trial. Here also trials are independent, like what we have seen in binomial distribution. What is the probability that all 3 servers fails within 5 requests? See here, interesting question. What we have to find out? We have to find out probability that all 3 servers fail within 5 requests. Fine. So, what is this? Means our we are interested in finding out our number of failures are fixed. What is the number of failures? Number of failures is the random variable here. Okay. So, we are interested in finding out x is, that is the my number of failures. It is, but it is given one second, assuming that each request represents what is the probability that all 3 servers fail within 5 requests. So, before 5 my all 3 servers should fail, okay, before or on 5. So, that means I am in my number of failures are fixed, that is 3 failures, and how many trials maximum? My trials will be 5. Okay. So, x is the, so my 3 servers may fail in the third request. My third failure I may get in the third request. My third failure I may get in the fourth request. My third failure I may get in the fifth request. Whenever I get the third failure, I stop it. So, my question was, what is the probability that all 3 servers fail within 5 requests? So, it has to fail within 5 requests. Within 5 requests means it may fail within third request, it may fail within fourth request, it may fail within 5 requests, isn't it? It definitely it cannot be less than 3, because there in one request there can be at the most 1 failure. So, if my third failure may be in the third request, so that is p of x is equals to 3. P of x is equals to 3. My third failure may be in the fourth request. My third failure may be in the fifth request. Okay. So, x is the number of requests. Okay, that is the random variable. So, what is the formula? What we have seen? So, just putting it in the formula, that is all, nothing else. Just if we put it, how do we put it in the formula? If my third request in the third failed, so that is x minus 1 by k minus 1. So, x minus 1 by k minus 1 into p to the power k 1 minus p to the power how much? K minus x. So, here it is 0. Similarly, my third failure in the fourth request, this is in the fifth request. So, that is negative binomial distribution. Okay. So, now this another type of distribution, which is also in the same angle, same direction, I should not say angle, same direction, that is geometric distribution. In geometric distribution, what we are interested in finding out the number of trials we need to get the first success. Here also my success is fixed, success is 1, just 1. In negative binomial, my success can be anything, but the success was fixed. Here also my success is fixed, and that is only 1. I am interested in finding out how many trials do I need to get the first success. The applicability first, let me tell you the applicability of this type of geometric distribution. Suppose you are installing some, a company is installing some telephone connectivity, and maybe we are interested in finding out when we dial a number, after how many dial we get the line gets connected. Okay. For dialing how many times and my line gets connected. I have tried it once, the line did not get connected. In a busy time, maybe I have tried it again, it did not get connected. I have tried it again, it did not get connected. So, suppose my line got connected in my fifth trial, that means the design, there has to be some problem with the design. No one will wait for 5 times dialing and then getting the connection. So, this sort of things, the geometric distribution is essential. Based on this, people can find out, so that there is problem in the line, and accordingly steps can be taken. So, there are many such cases where geometric distribution has great applicability. So, my first success, here also the random variable is the number of trials. Remember, always the random variable is that changes. So, you in any problem, first you need to find out what is the random variable. If you know what is the random, if you find out what is the random variable, then finding the probability will not be different. Then you will have to, then finding out which it falls in which probability distribution, whether it falls in binomial, multinomial, hypergeometric, negative binomial, geometric, what Poisson, whatever it is. First find out what is the random variable. So here random variable is the number of trials, and we were interested in number of trials, we get the first success. So the formula for this is here, the formula for this is quite simple. It is simple P of Q. So there are total X trials, isn't it? So in X trial we will get one success, that the last one is success, isn't it? So one success means that is P, and in rest X minus 1, that is the failure, and failure these are not distinguishable. So you do not have to do any combination or something like that. So it will be just simple Q to the power X minus 1. So simple, this is the formula P into Q X minus 1. Okay. So where X can take any value from 1 to 3, like means we can get the first success in the first trial itself, we can get the first success in the second trial. So X can take any value from 1 to 3. So that is geometric distribution. So problem, for a certain manufacturing process, it is known that on the average 1 in every 100 item is defective. What is it? On the average 1 in every 100 item is defective. That means this question, this particular statement, what it gives, this particular statement gives us the probability of defective items. What is the probability of defective items? 1 by 100, isn't it? Relative proportion. Probability of defective item is 1 by 100. Okay. So what is the probability that the 5th item inspected is the first defective item found? Okay. This reminds me, we can also, this sort of geometric distribution is also used in many kinds of drug survey. When we are before bringing a drug to the market, if we are interested in finding out, suppose if a drug we should get, for a drug to bring into the market, it should at least prove that it is 80% of the cases it is successful. So we will go on doing the trial till we find that it is showing 80% successful. Now this 80%, for getting the 80% successful, how many patients we have used this drug. So if this number of patients is quite large to get a 80% successful, then this drug, there is some wrong with this drug, then it should not be brought to market, it needs some more work on it. So this geometric distribution has also its use in that type of situation as well. Okay. Now coming back to this question, I just remember that example and I thought of mentioning it. Now coming to this example, so here the defective rate is given for a certain manufacturing process. It is known that on the average 1 in every 100 item is defective. Okay. So how much is defective it is given. What is the probability that the 5th item inspected is the first defective item found? Okay. 5th item inspected, first item we have inspected, it is not defective. Second we have found, it is not defective. 5th item we found, it is defective. What is that probability? Probability is geometric distribution is simple formula P into Q, isn't it? Simple formula P into Q, Q to the power X minus 1, right, where X can take any value, X can take value 1, 2, 3, any value. So we can find the first defective in the first trial itself. So this is, so here X is equals to 5, P is equals to 0.01, 1 in 100. So putting in the formula, that is the probability of getting 5th item inspected is the first defective found. Now there is one more, this is the last probability distribution that we will be discussing under the umbrella of discrete probability distribution. So Poisson distribution, there are some experiments which involve the occurring of the number of outcomes during a given time interval. Here, as in contrary to binomial distribution, here what we are, number of outcomes in a given time interval. Okay. There we are trying, in binomial distribution or its related negative or geometry, we are trying to find out the number of success in so many trials. Here what is that, which in the occurring of the number of outcomes during a given interval. A very good example is toll, where does the toll collection, where for highway we have this toll plaza, where we have to, when the car passes, we have to give the toll value. So we can say in a span of say 1 hour, how many car has passed the toll. Okay. Or in a particular highway in a span of some few hours, how many vehicle has passed. Okay. So, or in a ticket counter at a particular time, how many people are there in the counter in a particular time. So, this is similarly, suppose in a particular material, a material of particular size, say 1 meter, in a material of size 1 meter, how many flaws are there? Maybe flaws maybe in terms of design, flaws maybe in terms of density of the material, whatever. In a material of 1 meter, how many flaws are there? So, that is what, which involves the occurring of the number of outcomes during a given time interval, okay, or in a region of space. So, such experiments are called Poisson experiment. So, example, number of clients visiting a ticket selling counter in a metro station, as I already mentioned. Like here, one more thing, like number of calls coming to a call center at a particular time, that is also a Poisson distribution. But again, there is something like if you talk about a ticket counter, the people arriving in a people in the queue for a ticket counter, and during early morning or during peak time, it varies, isn't it? So, there are again different version of Poisson distribution to model this time, where it is dependent on time, where the number of people, where the average number of people coming to a counter, it is dependent on time, right. So, the average number of event occurring in a particular time interval. So, if it is dependent on time, then it is not a simple Poisson distribution, that we call it as non-homogeneous Poisson distribution, which we will not be discussing. This is a bit higher level. So, just for your knowledge, I just thought of mentioning it. Now, we are just considering the simple Poisson process. So, Poisson process has certain characteristics, certain quality we can say. So, what are those? The number one, the number of outcomes occurring in one time interval or specified region of space is independent of the number that occur in any other disjoint time interval or region. What is it? The number of outcomes occurring in one time interval or specified region of space is independent of the number that occur in any other disjoint time interval or region. In a highway, if in 1 hour total 100 car has passed, that does not mean in the next hour also 100 car will pass, or that does not mean already 100 car has passed, that means now only 2 or 3 car will only pass. That is not that. It is not dependent on what happened in one time interval, that will not dictate what will happen in the other time interval. Okay. So, this property basically this is as if it does not have memory. So, this property is called memorylessness property. So, again I am repeating, say number of outcomes occurring in one time interval is independent of the number that occurs in the previous time interval. Okay. So, it does not have any memory. So, next property is the probability that a single outcome will occur during a short time interval or in a small region in a very short time interval, okay, it is proportional to the length of the time interval. If the probability that a single outcome will occur in this highway, probability that a single car will pass, it is that probability actually it is proportional to the length of the time interval. There is no other thing that will dictate that. It is not that because 1000 cars have passed in the last hour, so just one car will pass in this. No, not that. It is proportional to the length of the time interval, or in case of space, it is proportional to the size of the region, and does not depend on the number of outcomes occurring outside this time interval or range or region. Okay. The third property, the probability that more than one outcome will occur in a very short time interval or fall in such a small region is negligible. If we consider a very small time interval, the more than one outcome will occur is very negligible. Okay. So, these are the three properties of Poisson distribution. Now, what is the function of Poisson distribution? And Poisson distribution, we have a parameter, that is we call it lambda, where lambda is the average number of outcomes per unit time, average number of cars passing through that highway in 1 hour, average number of cars passing the toll station in 1 hour or in 24 hours, whatever it is. So, that is the parameter, that is lambda. So, x is the number of cars that pass the toll station, or number of cars that pass the highway, or number of flaws in the material of 1 meter, whatever it is, that is the x, that is the random variable. X is the random variable, lambda is the average number of outcomes per unit time, and t is the total time interval that we are considering. Okay. So, lambda is given suppose in terms of 1 kilometer, and suppose we need to find out in terms of 10 kilometer. So, that is t. So, what is the formula for that? E to the power minus lambda t into lambda t to the power x factorial. This also like how we have calculated for uniform probability distribution, binomial, whatever what we have seen, we could easily calculate it from our knowledge of probability theory, isn't it? What we have learned from probability theory, permutation combination for finding out the sample space, we could easily find out the function. Similarly, for Poisson distribution also, if we go step by step, you can easily find out, deduce this expression, but that is not necessary. That is not, if you are interested, you can do it by yourself, there is no issue, but this is the function for Poisson distribution. F of x lambda t is nothing but e to the power minus lambda t to the power x factorial. These things are so actually so common, it will be in the tip of your tongue always. Once you learn it, you will never forget it. So, now one small example. Electrical power failure at a particular location occurs with an average frequency of 1 in 24 hours. Okay. What is the probability that there will be 2 or more failures in 24 hours? What it is given? Average frequency is 1 in 24 hours. That means lambda is 1 per 24 hours. Okay. Now, what we need to find out? What is the probability that there will be 2 or more failure in 24 hours? 2 or more failure in 24 hours. My t is 24 hours, and I have found in lambda also 1 in 24 hours. Okay. So, my lambda t is just 1. Okay, lambda t is 1. Now, my x is a random variable. What is the x? X is the number of failures. I am interested in finding out 2 or more failures. That means, what is the probability of finding out 2 or more failures? In the it is basically same as finding out 1 minus of 0 failure plus 1 failure. 0 failure, 1 failure means at most 1 failures, that is 0 plus 1. If I subtract 1 minus of that, then I will getting 2 or more failures, because or else I have to find out 2 failures, 3 failures, 4 failures, it might go to infinity. So, that is difficult to find out. Instead of that, I will take the easy path, that is 1 minus 0 plus 1. Okay. So, what is probability of x is equals to 0? So, putting in the formula e to the power minus lambda t to the power x factorial. Okay. So, we found out x is equal to 0, we found out x is equals to 1. So, for x greater than 2 is minus 1 minus of these two values, that is all. Okay. So, one more example here we have, a nuclear plant receives its electric power from a utility grid outside of the plant. From past experience, it is known that loss of grid powers occurs at a rate of once a year. Okay. A nuclear plant receives its electric power from a utility grid outside of the plant. Okay, fine. From past experience, it is known that loss of grid power occurs at a rate of once a year. So, that is lambda. Average is once a year. Lambda is 1 per year. What is the period over a period of, what is the probability that over a period of 3 years, no power outage will occur? Now, my t is 3 years. Lambda is 1 per year. My t is 3 years. I am interested in finding out what is the probability over a period there is no power outage. That means, I am interested in finding out probability of x is equals to 0, given lambda is 1 and t is 3. Simple, just put it in the formula, lambda is equal to 1, t is equal to 3, x is equal to 0, fine. Now, next question is, at least 2 power outage will occur, at least 2. That means, it can 2, 3, 4, anything. So, similarly, now 1 minus 0 plus 1, that will give me at least 2, isn't it? So, that is why here see we found out x is equals to 0, we found out what is x is equals to 1. So, 1 minus x is equals to 0 minus x is equal to 1 will give me x greater equals to 2. Okay. So, now to summarize the descriptive measures, but for all the probability distribution that we have seen. First, properties of the discrete probability distribution, what we have seen, a value of f x will lies from 0 to 1, that we have seen what is f x. F x is the probability at point x, at value probability of x, then summation of f x is equals to 1, mean is equals to x f x, summation f f x, variance is equals to summation x minus mu whole square f x. We have already seen all this. Now, for discrete uniform distribution, we have seen f x is equals to 1 by n if the value that x can take is 1 by n. Then if we find out mu is equals to k plus 1 by 2, variance is k square minus 1 by 12. Just putting it in a formula, you will get it. And again, you do not have to put it in a formula and evaluate it, you can just remember it. It is just like a plus b whole square. Do we need to do it and solve it and do it? We can remember a plus b whole square is equals to a square plus 2ab plus b square. Similarly, you can dissolve these things also, it will be in your memory always. Similarly, for binomial distribution, what is the mean? Mean is np, variance is npq, 1 minus p is q. So, for hypergeometric distribution, mean is, see here, mean is for hypergeometric, we have also done one problem also. Mean is what? N into k by n. What does k by n symbolize? K by n, I am writing it here. What is k by n? K by n is nothing but is equal to p. Out of n, out of capital N, k are success. So, what is this? This is p basically, isn't it? So, n into, so mu is equals to basically n into p. So, hypergeometric distribution mu and binomial distribution mu is same. Binomial distribution also mu is np, here also mu is np, because k by n is nothing but p. And in sigma also, same for binomial distribution, what was my sigma square? Sigma square is npq. Here also you see this is n, this is p, this is q, 1 minus k by n is q, but we have just one extra term here, that is n minus n small n by n minus 1. Okay. Now, one thing, now if our size of n is very big, capital N, and small n is very small, what happens? Like from a what to say, bucket of water, if I bring out one glass of water, will it make any difference? It will not make any difference, right? It will be hardly it will make any difference. From a bucket of water, I am just bringing out one glass of water. But if in a small bowl where I am putting say 2 glasses of water or 3 glasses of water, from there if I pick up 1 glasses of water, there it will make difference. So, that is what here you can see in the hypergeometric distribution, this value n minus n, this value n minus n by n minus 1, this will make a difference when my capital N is not very large and small n is also not very small, then only it will make a difference. Else if my capital N is very large and small n is very small, that means n minus n by n minus 1, it will be almost equivalent to 1 only, it will not make much of a difference. Okay. Then it turns out to be same as binomial distribution. Why I mentioned this? For very large n, large capital N, total size of the sample, and very small n. So, instead of using hypergeometric distribution, we can use binomial distribution as well, because we have seen it hardly makes any difference. Mu is same, sigma is sigma, we have just another one extra factor here, that is n minus n by n minus 1, but when n is large, small n is small, the difference is not reflected at all. So, we can for very large n and very small value of the sample size, that is small n, we can use, instead of hypergeometric, we can use binomial distribution as well. When the case is suitable for hypergeometric, that means without replacement, but still we can use binomial. That is the example. From a big bucket of water, bringing one glass will not make any difference. So, similarly for Poisson distribution, mean is lambda t and variance. For Poisson distribution, mean and variance both are same, that is lambda t. Okay. So, now to conclude this lecture, in this lecture we have discussed negative binomial distribution, geometric distribution, Poisson distribution. We have also seen the descriptive measure of different probability distribution. Again, I request you solve as many problems as possible, so that you become confident in all these distributions. And in this next lecture, we will cover a tutorial on this discrete probability distribution. And the references, and thank you guys.